Hello and welcome to part 3 of lecture 18. In this part, we're actually going to kind of look at an important theorem right here written in black that says that when you're looking at a finite dimensional vector space over the complex numbers, and if you take a linear operator, then you can actually find a basis so that that matrix that you get, the associated matrix to the linear operator, is upper triangular. Now this is kind of a long proof. It will actually take the whole part of this lecture, but I'll walk you through it as slowly as I can and with as much detail. Now the proof is by induction on this dimension of the vector space. So you want to think of, we're going to look at first the vector spaces of dimension 1, and then we'll look at vector spaces of dimension n, and we'll reduce the problem to looking at a vector space of dimension n minus 1, so we can apply induction. So let's look at the base case. Let's first assume that our vector space is one-dimensional, and then you can take any vector v to be a basis for v, right? So with the assumption, of course, that with v not equal to 0, then that actually will form a basis for your vector space. And take any linear operator on this vector space. And then what you know is that when you plug v into t, you get another element in v, but because v, the basis for v, the basis for capital V is little v, you get that tv is equal to some constant v for some c inside of your field C. Okay, so we have this. And so you want to sit down and think about what is the associated matrix when you're dealing with a one-dimensional space? Well, you're getting a one-by-one matrix. And in that one-by-one matrix is just going to be the value of C. And it turns out that this is considered an upper triangular matrix. So this is an upper triangular matrix. So the base case is true. Okay, and it just follows from what I've just explained right here. So let's look at the case where we're assuming now that our vector space has dimension greater than 1. And what we're going to do is assume that the result holds for any vector space W, provided that the dimension of W is greater than or equal to 1, but strictly less than n. Okay, so now what can we say? Well, since V is a vector space over the complex numbers, we proved in last class that V has to have an eigenvalue, okay? Then T inside of LV has an eigenvalue, okay? So that's going to be kind of important here. And again, now we're going to see what this is kind of really why we need to work over the complex numbers so that we can justify that it has an eigenvalue. And let's call it lambda. And now what we're going to do is consider the linear map. We're going to look at a special linear map, and that linear map is the map t minus lambda I from the vector space V to itself, okay? And you just want to remember what this means is given by, how does this function work? Well, I plug in V, and as output, I get TV minus lambda IV. Okay, or another way of thinking about it is I get TV minus lambda V. So this is my new linear map. And what we want to do is we want to let U be the range of this map. Okay, so maybe as a little picture here at the top, right, you have your vector space V, and you're going over to your vector space V. Your map, you're looking at a map from T of the form T minus lambda I, going from V to V. And inside of it is the range. Okay, so that's going to be the U. Okay, that's my U. Okay, so that picture might help. And now, because we know that lambda is an eigenvalue, the dimension of the null space of this operator has to be greater than or equal to 1. Okay, so that implies that this dimension, this new subspace is less than or equal to n minus 1. And why is that? Well, that follows from the properties of the fundamental theorem of linear maps, because we have that the dimension of the operator t minus lambda I, the dimension of the null space of that operator, plus the dimension of the range of that operator, so which is the dimension of u, has to be equal to n. So because this guy is greater than or equal to 1, this has to be less than or equal to n minus 1. So in terms of the picture, what it means is that u is sitting inside of v. Okay, it's properly sitting inside of v. And why is that important? It's because we want to say something about this space right here by induction. Now, what else can we say about this space U? Okay, well, it turns out that this subspace is invariant under the operator T. Okay, and to see why this is true, let's say you take an arbitrary element, little u, inside of the space U, and you plug it into your function T. Now, it turns out, right, that we could re-express this as Tu minus lambda u plus plus lambda u. So we're doing our favorite mathematical trick of adding in 0 in a special way. And notice that this is the same thing as t minus lambda I evaluated at u plus lambda u. Okay, and let's think about what these various pieces are. Okay, well, then obviously lambda u is inside of u because u is inside of u, and so any scalar multiple is inside of u. This is a property of a vector space. And by definition, t minus lambda I, u has to be in u, which is equal to the range of t minus lambda I. So these two pieces belong to u, so that means the whole thing has to belong to u. So Tu is inside of U, okay? And the reason here is since U is a vector space, right? So we get this property going across. Okay, so now, remember U is sitting inside of V, and we can talk about the restriction of T, okay? And that continues to be a linear operator, okay? So let me kind of rephrase that here, or add some more detail. Okay, i.e., we can look at the map T going from, what I wanted to say, sorry, let me rephrase that, and saying that T restricted to U is a linear operator on U. So in terms of the picture here, you want to think of, U is sitting over on this side as well. So you can think about if we take the map T going between V and V and we restrict it to U, it would take U to within side of U. That's what's happening there. Okay, so we have this linear operator on this subspace, and we know that U has smaller dimension. So by induction, there's a basis U1 through UM of U such that the matrix associated with the linear operator is upper triangular. Okay, so i.e., using the properties of what it means for a matrix to be upper triangular, that means that this basis has to satisfy the property that when you restrict to U of T, evaluated at uj, this is inside of the span of U1 up to uj for j equaling 1 through m. Okay, so just a little clarity here. Because it's upper triangular and U1 through UM is the basis for U, we have this fact right, I don't know if you can see that there, we have this fact right here, and on the restriction to U, that's the same thing as TUJ. Okay, so you want to think of, going back to my picture, there's a little u here and going over to u here, and if we look at the map just on that U part, then there's a upper triangular matrix associated with it, but that's only on U. Right? And so we have a basis U1 through UM of U, and what we now want to do is extend that basis to all of V. Okay, so say we extend it to U1 up to UM, and then we add in, we're not sure how many vectors we have to add in. We definitely have to add at least one more vector, but we can extend it to a basis of V. Okay. And now our strategy is to show that for each of these basis elements, it's going to satisfy the properties that this is going to be the basis that allows us to create an upper triangular matrix. Okay, and now let's check that. Now for each k, what do we have? Well, we're going to do our same trick again, that we can add in 0 in a nice way. So this is the same thing as tvk minus lambda I vk plus lambda vk. And then this is the same thing as taking the operator t minus lambda I, evaluating it at vk, plus lambda vk. Okay, and now what do we know about this? Well, we know that this guy here is in the span, is in U. So now t minus lambda I vk is inside of U, which is inside of the span, which is in the span of U1 up to UM, because U1 through UM is our basis of U. Okay? So putting the pieces together, we have that tvk is inside of the span of U1 up to UM, V1 up to VK. Okay, and so the basis U1 through UM, V1 to VP satisfies property 2 of the theorem on upper triangular matrices that we proved in the last video. Upper triangular matrices. Okay, and so because it satisfies property 2, that means that i.e. the matrix MT is upper triangular with respect to this basis. And that's exactly what we wanted to show. Okay, so just to recap, go back to property 2 here, just so you can see it. Right here is you're having a basis, and you have to show that each time you take, you kind of do this one at a time, right? You would want to show that TV1 is in the span of V1, TV2 is in the span of V1 and V2. So in our case, we're looking at the basis U1, UM, V1, VP, and like U1 is in the span of U1. U2 is in the span of U1, U2, right? That's part of all the induction. So the induction tells me that all the UIs are in the right thing. And then above, we're showing that as we add the V's, we continue to have that property. So that kind of finishes the proof. Now I know this is probably a complicated proof, and there's actually a bit of a downside to this proof, but it's not the worst part. But I just want to point out the proof is an existence proof. Okay, so it does not show us how to find the basis V1, V2 up to Vn. The proof just shows us that there is a basis, but it doesn't actually give us any hint on how to find the basis. So I hope that helped when you're reading this section. In the last part, we'll talk quickly about some consequences.